state and prove Taylor's theorem, which also I would consider a fundamental result in real analysis. Okay, so before we state Taylor's theorem, I'm going to set up some notation, right, and give some informal background to Taylor's theorem. So first, for notation. So the notation we will follow is that f with a superscript bracketed n of x denotes the nth order derivative of f. What do I mean by nth order? You do an n-fold derivative, right? You take the derivative, then the derivative of the derivative, and so on, and you take the derivative n times. Okay, so in particular, f1 of x is what we have so far been calling f prime x, and as a matter of convention, f0 of x, right, when I put 0 as the order of the derivative, that's just the function itself, right? That will just help us write Taylor's theorem more compactly. Okay, so that's our notation. With this, the Taylor expansion is given as follows. Okay, for a function f that is, let's say, n times differentiable at, let's say, some point C, the following is known as the n-1th order Taylor expansion. So summation k running from 0 to n-1 k of x minus c raised to k by k factorial. Okay, this, and we'll interpret this in a bit, is called the n-1th order Taylor expansion of f around C. Okay, now this n is basically any natural number, so n is greater than or equal to 1. Okay, so let's interpret this. So as an example, if I take n to be 1, in other words, the 0th order Taylor expansion would have just a single term in the summation, which would essentially be f of c. Okay, so the 0th order Taylor expansion is just the constant function f of c, right? Just takes the value of the function at c. The first order Taylor expansion would be f of c plus f prime c times x minus c. You can see that this is in fact the equation of a straight line which intersects the function f at the point c and has a slope which actually matches the derivative of the function at c, right? So this is would also be commonly referred to as the tangent line on the function f at the point c, right? Similarly, the second order Taylor expansion would be given by f of c plus f prime c times x minus c plus the second derivative f prime prime c times x minus c the whole square by 2 factorial, which is 2, right, and so on, right? So the second order Taylor expansion, you can see, is in fact a quadratic in x. So in general, the thing to notice is that the n-1th order Taylor expansion of f would be a polynomial of order n-1, right? So in general, these different Taylor expansions can be really thought of as polynomial approximations. of the function f near C. So polynomial approximations of f near C. Right? So that is exactly what the in general the n minus 1th order Taylor expansion is. It is an n minus 1th order polynomial approximation of the function f in the neighborhood of C. Right? So that is the way to interpret the Taylor expansion. Okay. Now a natural question would be, what is the error associated with this approximation, right? Right, and in fact Taylor's theorem gives you some answer, gives you an answer associated with the error associated with the Taylor expansion, right? So specifically we will denote the error as Rn of x. So Rn of x is the error between the function and its n minus 1th order Taylor expansion. In other words, Rn of x is defined as follows. It's f of x minus summation from 0 to n minus 1 fk of c. Oh, I think I made an error here. The kth derivative has to be at c, of course. Yeah, I mean all the examples I've given are correct. Just the Taylor expansion, yeah, involves derivatives at c. Okay, so fk of c times x minus c raised to k by k factorial. Right, so the error between the function and its n minus 1th order Taylor expansion is denoted by Rn of x, and Taylor's theorem gives you a characterization of this. Okay, so the broad idea of Taylor's theorem can be thought of as follows. You have a function, some arbitrary function, but it has to be sufficiently differentiable, right? For example, to even define the n minus 1th order Taylor expansion of f around C, the function needs to be at least n minus 1 times differentiable at C, right? Just to define it, right? Because it's at the n minus 1th order Taylor expansion of f around C is an n minus 1th order polynomial, the coefficients of which are dictated by the derivatives of the function at C. Okay, and the error associated with this approximation, the n minus 1th order Taylor expansion, is what is denoted by Rn of x, and that is what we will characterize essentially as part of the statement of Taylor's theorem. So that comes next. So here is the statement of Taylor's theorem. Okay, so the hypothesis says that the function f is defined on some open interval ab. In particular, there's nothing that stops you from taking a to be minus infinity and b to be plus infinity. C is some point in this interval, and suppose that f is n times differentiable on this interval a comma b. All right, then for x which is not equal to c, and n greater than or equal to 1. Well, this n is here, right? So this n is greater than equal to 1. Right? The following is true. F of x is equal to, it's n minus 1th order Taylor expansion. So that's k going from 0 to n minus 1 fk of c right, plus, and this is going to be the error term, the nth derivative at some point y times x minus c raised to n by n factorial, where y lies between x and c. Okay, and this is really what we have been calling Rn of x, right? The error associated with the n minus 1th order Taylor expansion. So once again, the function has to be n times differentiable, n greater than equal to 1. In that case, for x not equal to c, okay, the function is equal to the n minus 1th order Taylor expansion plus Rn of x, which is the error associated with this approximation, where Rn of x can be expressed as follows. It is essentially going to be x minus c raised to n by n factorial times the nth order derivative of f evaluated at some point y that lies between x and c. Okay, so this is the characterization of the error term that is provided by Taylor's theorem. Okay, and we'll see how to use and interpret this error going forward, but first we will look at the proof of the statement. Okay, before I get to the proof, one thing to note is that if you take n to be 1, right, this statement is exactly the same as the mean value theorem. Right, because recall that the mean value theorem tells you that f of x is equal to f of c. This is indeed the 0th order Taylor approximation plus f prime y into x minus c. Right, the existence of a y such that f prime y is equal to f of x minus f of c upon x minus c is exactly what the mean value theorem says. Okay, now another thing to note is that from as will become apparent from the proof going forward, Taylor's approximation in fact does boil down to a repeated approximation, a repeated application of Rolle's theorem. Remember that the mean value theorem is just a trivial generalization of Rolle's theorem, right? So what we are illustrating here is if n is equal to 1, Taylor's theorem follows from a trivial application of Rolle's theorem after all, right? Which is what is precisely the mean value theorem. As we will see, for any general n as well, the statement of Taylor's theorem will in fact follow from an n times repeated application of Rolle's theorem. Okay, so this is this connection for n equals 1 is not an accident. Okay, so now let's get to the proof. Right, now first we say let M be the unique solution of the equation f of x is equal to summation from 0 to n minus 1 fk of c that's your n minus 1th order Taylor expansion plus m times x minus c raised to n by n factorial. Right, now this is an equation that is linear in M, so it is in fact going to have a uniquely defined solution, right? So let M be defined as the solution to this, right? What we want to show is that there exists some y between x and c such that M is in fact the nth derivative at y. So we want to show that there exists a y between x and c such that m is equal to the nth derivative of f at y. Okay, so this is what we want to do. In order to do this, we are going to define this new function g as follows. So g of t is equal to, well, 0 to n minus 1 fk c t minus c raised to k by k factorial plus m times t minus c raised to n by n factorial. Right, this as a function of t, the first term here is basically as a function of t, the again n minus 1th order Taylor expansion. The second term is in fact the correction term, right, that we are hypothesizing. We have written it in terms of a generic constant m times t minus c raised to n by n factorial, right, minus f of t. Okay, so this new function g has been defined as follows. If you should expect that such a function is defined if you go back to the proofs of Rolle's theorem and mean value theorem and so on, right? Specifically, the mean value theorem did define such a function g. Okay, so now the thing to note is the following, right? And this is in fact the crux of the proof. If you look at g evaluated at c, it is in fact 0, right? Because all but the first term of the Taylor expansion will become 0 because there's a t minus c raised to something. So the first term of the Taylor expansion would basically give you f of c minus the last term giving you another f of c, right? So g of c is 0. However, properties of g go further. If you look closely, you will realize that g prime c is also equal to 0. Why? Because when you differentiate g of t, the first term would basically end up boiling down to the first derivative of f at c, and that in turn would cancel out the last term. All the other terms would drop off to 0. You further differentiate g, you will still get that it is in fact the second derivative is also 0 at c. In fact, all the way up to the n minus 1th derivative at c, all of these guys are equal to 0 by construction. Okay, so g is constructed in this fashion, and moreover, if you look at g of x, right, g of x, if you think about it, is also 0, and the reason it is 0 is by definition of m. Okay, so we have a function g that we have just defined. The zeroth all the way up to n minus 1th order derivative at c is equal to 0, and g at x is equal to 0. Okay, so this is what we need to essentially complete the proof. Okay, so now let's maybe draw a picture on this side for a moment. This is c, and let's pretend that x is to the right of c. Okay, now since g of c is equal to g of x is equal to 0, there exists x1 between x and c such that g prime x1 is equal to 0, right? This follows from Rolle's theorem. Right? So g is 0 at both x and c, and so therefore there must be an x1 which would, let's say, be somewhere here, where g prime x1 is equal to 0. Right? Next, we apply Rolle's theorem again by noting that the first derivative at c is also equal to the first derivative at x1, which is equal to 0. Remember, g, the first derivative, the second derivative, all the way up to the n minus 1th derivative at c are 0. And by the first application of Rolle's theorem, I realized that x1 has also the first derivative 0. Right? Now since I have this, by another application of Rolle's theorem, I would conclude that there exists an x2 between C and x1 such that g prime x2 is equal to 0. So maybe this is x2. Okay, now you can imagine where this is going. Since the second derivative of g at C and the second derivative of x2 at C is second derivative of g at C and second derivative of g at x2 are 0, there exists an x3 between these 2 points where in fact the third derivative would be 0, right, and so on, right? So this would go on until one can say that there exists xn between C and xn minus 1 such that the nth derivative at xn is equal to 0. So these points essentially keep moving in this direction, and this is, let's say, xn, right? Note that to show the existence of this xn, you needed to show that the n minus 1th derivative of g at C and the n minus 1th derivative of g at xn minus 1 are both 0, right? That is what finally gives us the point xn. Okay, now we go back to the definition of g and in fact check that the nth derivative of g at xn is in fact exactly the same as m minus fn of xn, right? In other words, the point xn that we have found is in fact the point y that we were interested in, right? In other words, the characterization of the remainder of Taylor's theorem is in fact correct, right? There does in fact exist a point y between C and x such that the error can be expressed as the nth order derivative of the function f at y times x minus c raised to n by n factorial. Alright, so that is how you prove Taylor's theorem. If you think about it, it is basically boiling down to, just as the mean value theorem follows from a single application of Rolle's theorem, Taylor's theorem follows via an n-fold application of Rolle's theorem. Right, so that's the proof of this. What we will do in the next video is basically interpret the Taylor expansion and say something about how the error behaves as the number of terms involved is increased.